Good afternoon, everyone. Before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. And if we would like you to introduce yourself, your name, designation, and the country you are based in. Thank you for confirming. It's a pleasure to see an international audience of people from all industries and backgrounds. It's our pleasure to see you all. Great. Thank you so much. I am getting your confirmation messages. I would like to thank you all for registering and taking time out on a Sunday to learn about indirect examination techniques for buried pipelines, including DCVG and CIP surveys. My name is Aisha Khalik and I will be your introductory speaker for today. It's our pleasure to host this webinar for you. This is our 105th webinar in the series of technical webinars that we are conducting. As a practice, Velosi is conducting one webinar every month. So please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates. Today, we have an experienced panel of speakers. I am with Mr. Ijazul Karim Rao, who is Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatun, she is Director, Engineering Services. Mr. Anthony James William, who is General Manager, Global Sales with us, and myself. Moving forward during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on the topic. You can type your queries in the question and answer window and not the chat window. And you will receive a reply in the question and answer window, or we can take your answer live. We will try to answer as many questions as possible during this session, as we'll have to also have a detailed question and answer session at the end of the webinar once we complete the topic. Please accept our apologies if your question is not addressed due to high volume of the queries that we generally receive. So we have to be selective. Furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and also have shown their participation through question and answer during the webinar. So since this is a quite technical subject, we will touch only the key theoretical and practical aspects of indirect examination techniques for buried pipelines, including DCVG and CIP survey. Before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those who are around us. So today we will be covering velocity introduction, then our main topic, that is indirect examination techniques for buried pipelines, standards and regulations that are related to this topic, and then we will close with case studies overview, and at the end we'll have a question and answer session. Velosi is the leading global consultancy firm that provides asset integrity management, HSE, engineering, and software development solution services to clients in the oil and gas, energy, power, and petrochemical industries around the world. We also have our in-house proprietary software, WhalePlan, which is an industry-leading SAP-certified complete asset integrity solution, currently being used by oil and gas giants such as ADNOC, TANUP, BSR, GOTL, ENIC, NAVA, and etc. Founded in 1982 in Malaysia, Velosi Group was then acquired by Applus Velosi in 2011. We, with about 44 plus years of experience, we have expanded our footprints in more than 86 countries so far. We have completed 1,400 plus projects with 550 plus customers. Our areas of expertise include, but are not limited to, asset integrity management, HSE environment and environmental services, engineering services, AI and software development services, and training services. So here is a map that shows our worldwide existence of our corporate offices, head offices, and our associate offices throughout the world. We provide services covering a broad range of industries, including but not limited to oil refineries, GOSPs, and gas and NGL plants, chemical plants, fertilizer plants, infrastructure, structures, wellheads, offshore platforms, and pipelines. Now, I will just give a brief overview of our services. So first of all, asset integrity management services. Under these services, we are providing RBIs, PIMS, PIMS, ISMS, WIM, asset performance management systems, computerized maintenance management systems, SAIL, safety integrity level studies, etc. Then we have health, safety, and environmental services, under which we are covering HSEIA studies, process safety and risk studies, environmental studies, occupational health risk assessment, OHRA, which include quantitative, qualitative OHRA. Then we have engineering services, under which we are providing conceptual design feed, operating manuals and procedures, design verification and appraisal, fitness for services, and as-built drafting services. Then under software solutions, we are developing softwares, and so far we have developed WhalePlan, which is asset integrity management system, Whale PHA for process hazard analysis, Whale PSRA for petrol station risk assessment, Whale MTS for material tracking systems, Whale ORP, online reporting portal, and Whale feedback. We are also providing audit and assessment services where we provide consultancy services and audit services like OSA safety audits, technical audits, environmental audits, PSM audits, structural audits, and under consultancy services and trainings, we have so far completed ISO 9001, which is quality management system. Then we provide consultancy services for ISO 14001, which is environmental management system, OSAS 18001, ISO 45001 for occupational health and safety management, ISO 50001 for energy management, and ISO 55001 for asset management systems. We also provide various trainings through our Velosi Training Institute, LLC, established in Abu Dhabi. And so far, we have completed certified technical trainings, exam preparatory trainings, HSC trainings, NIBOSH, IOSH, admin and business related trainings, food safety trainings. Contact us if you also require any of these trainings. Now coming towards Whale Plant. Whale Plant is a leading fully industrial standard certified asset integrity software solution. And it is built on modular framework, which means it has multiple modules which address the asset integrity of different equipments, like pressurized equipments, structure integrity management system, PIMS for pipeline onshore and offshore, PSPMS, electrical instrument rotary management system, wellhead integrity management system, etc. Our Whale CMMS is a powerful tool that keeps tracks of information about an organization maintenance operations and facilities to make informed decisions by planning, scheduling, executing, and optimizing maintenance operations, resources, and materials within same software. Whale AIPS, which is an asset integrity process safety management system. It's a comprehensive process safety management system designed to improve safety and regulatory compliance within industrial sectors. Then we have also developed Whale ERP, which is a modular enterprise platform custom built and tailored industry-wise, serving multiple industries, including but not limited to trading, manufacturing, education, healthcare, and more. This is the main portal of Whale ERP, where you can see multiple verticals. Once you have selected any vertical, say for example trading, you will only find the modules related to that particular vertical. So Whale ERP Trading Suite optimizes end-to-end trading operations with real-time controls, for example, procurement, finance, and customer relationship management. So you can see multiple modules. Every module relates to this particular industry. Then if you select any of these modules, say for example, customer relationship management, CRM, empowers businesses to manage leads, track opportunities, and strengthen customer relationship through automation. Then our Whale PHA, which is process hazard analysis software, as the name suggests, it consists of various modules related to process hazard analysis. The modules include Whale hazard, SIL, and what if analysis. So we have also introduced Sara, which is our voice recognition assistant within our softwares, which simplifies the workflow. It allows hands-free navigations. It provides real-time insights, manages tasks within minimum human intervention. And also we have the established AI chatbot within our softwares, which retrieves data on voice command or chat. So for engineering services, we definitely utilize multiple types of equipments. Some of the equipments include magnetic flux leakage, cracking thickness measurement, ultrasonic pulse velocity, ultrasonic flaw detectors, and others. So as I mentioned before, that we have completed more than 1,450 projects with 550 clients worldwide. So this slide shows some of the clients which we are very proud of working with: ADNOC, Dragon Oil, Baroge, Lukoil, BSR, Repsol, Babco, PPL, and others. So this slide shows some of the Velosi certifications. We are certified with ISO 55001, ISO 27001, ISO 45001, and our Whale plant is certified with SAP for integration, two-way communication of data from SAP to Whale plant and vice versa. And the second, we also have certification from ECDA for our compliance with API 580. Some of the Velosi accreditations and approvals that we have from multiple organizations. Now, I will request Mr. Ijazul Karim Rao to start with today's topic.
Assalamu alaikum and good day, everyone. Today's topic is interesting one, but it's a big topic, so we have to concise our discussion to the maximum to the focus on the topic. And as general, today's topic is indirect inspection of the buried pipelines. So why we have to do inspection? There are integrity issues, there are corrosion issues, internal, external, and these two topics correlate with the integrity and asset integrity subject. So, what is integrity? As such, integrity means personal integrity is also a subject. A person should be honest, dedicated to the work, should not be able to do any non-compliance activity, right? So, integrity in terms of justice mean proper justice to the everyone. In general, integrity is a definition-wise a state of being unimpaired. It should not be. It means the quality of any particular subject is being undivided. Now, pipeline integrity assessment is a process by which above ground or buried pipeline is maintained in an unimpaired state, capable of safely transporting a product. So this is the integrity in terms of definition. Now, what is asset integrity? Which is generally we categorize into three aspects. Like first, design integrity. Like when pipeline is being designed or asset is being designed, it should be designed in accordance with international codes and standards and to meet efficient, reliable, and safe operational objectives. Technical integrity means once pipeline is designed and built and put in operation, then we need to manage it effectively. Means it is a inspection, it's a maintenance, and it's a general integrity management activities are being done in a proper way. Whereas operational integrity is a pipeline to be operated in accordance with the operating manual and procedures by trained staff and within the integrity operating windows of the pipeline or its assets, whether it's involving pumping, it's involving compression, and any upstream assets, any downstream assets, and pipeline itself. So that will be covered under operational integrity. See why this integrity is important. Why integrity operating management is very important for the assets. So there are incidents on the assets. In October 1998, in Nigeria, there was one major pipeline incident where 500 people were killed. Then in 1984, in Mexico, there was a pipeline incident causing 650 fatalities. In 1989, Russia, there was also a LPG pipeline and it also got ignited by the pipeline, by the trains, other impacts. 645 people were killed. There is another incident, 18 January 2019, a pipeline transporting gasoline exploded in town of Teolipan in Mexico, and it also killed 137 people. There is another incident, West Virginia. There was a damage to the houses and people were affected. Now, the common causes of failure, general, it is external interference or third party damage, like if somebody is sabotaging the incident or maybe somebody else actions have caused problem for the pipeline. Then corrosion, both internal and external. Then material component failure. For example, there are valves, there are flanges, there are compressors or pumps which might be causing the problem. Then operational and human error, like a plant is or pipeline is being operated by the operation team, they might be making some mistakes. Then natural forces, for example, if there is a soil movement, earth movement, or soil displacement, or soil movements due to earthquake, due to flood, due to tsunami, or there could be like a snowfall and more rain or more floods. So these are landslides, like landslides, earthquakes, and other kind of things may cause some problem for the pipeline integrity. So we know that pipelines got certain issues. How we can preemptively predict these issues? So as long as the natural forces are concerned, so we have the past 100 years history of that particular area, and it is assumed that pipeline should be designed to meet the worst scenario applicable in that particular area. And then, like if a pipeline is designed, especially 31.4 or ASME B31.8 gas pipeline. So there are safety classes, like it may class 1, class 2, class 3. The more conservative design is class 1, where the allowable stresses are, let's say, almost 1/4 of the tensile stress, or it could be 66% of the yield stress. So this could be a scenario of selection of the, like if a line is passing in a more dangerous area, the wall thickness should be more. If less dangerous area, the thickness could be lesser. So then stress analysis is done. All the external loads are implied or applied on the load stress analysis, and we see that if the pipeline will be able to withstand the applicable loads. That is the design side. Then the construction also is done in the same way. Then in the part of design, internal corrosion prevention by proper material of construction selection. Then external corrosion, that is managed by coating CP type, and also like if there are crossings, then third party should not be able to damage it. Right of the way management, and generally ASME B31.8S requirements are met, or API 1160 pipeline requirements are met. Direct and indirect techniques for the buried pipelines, our focus is mainly on the buried pipeline today. Otherwise, there are like above ground pipelines, there are subsea pipelines. So service-wise, pipeline could be in three categories: buried, above ground, and subsea, under the sea or under the river. So now there are techniques which are used for the once pipeline is put into operation. There are direct inspection techniques, and there are indirect inspection or assessment techniques. And design aspects like a design integrity, how the pipeline should be designed in accordance with the basically the requirement of that particular area of the land where the pipeline would be passing, whether it would be desert, whether it's mountainous, whether it would be river, marshy area. So we have to take care of the external situation and how it would be impacted by the environment or the environmental like disaster or surprises, for example, heavy floods, earthquake impacts, landslides, snowfall, and so on. Important thing is we have to consider the worst scenarios. We cannot take risk for the billions of dollars investment if anything would be basically affected by the just a moment of the pipeline, right? Okay. So now, what are the direct techniques? In general, and direct inspection, see, our focus is main on the inspection and integrity assessment, not operation, not design at this stage. So direct technique, there are ILI, intelligent pigging, there could be direct execution of the pipeline underground, and then you can do the thicknesses measurements, and then we can look at the condition and what kind of corrective action to be taken. And so direct assessment is easy. But if the pipeline is underground and ILI practically is not doable, or ILI may not be reliable. So in that scenario, so if the internal defects can be assessed based on the corrosion modeling, like if a dry gas line, it should not have any internal damage mechanisms. However, there are pipelines which are carrying a corrosive service, so that may have internal corrosion issues. If the internal corrosion issues are there, those has to be managed by process control, by corrosion inhibition, or by changing the constituents of the fluid. So that is a process control issues. So, however, if there is external corrosion issues, those are managed by proper coating system, CP system, and proper inspection and maintenance of those supporting facilities. So now, if we wish to assess a pipeline, so there would be direct techniques and there are indirect techniques. Indirect techniques mean pipeline is underground. We are not executing the pipeline and we are not touching the pipeline, but still we can see if the external corrosion damage mechanisms are under control. So those techniques, normally we follow DCVG, CIPs, ACVG. Then by qualitative assessment of these techniques, then we can say screen the pipeline where it could be a problematic area. Then in that problem area, we can excavate and then assess what is the condition. Examination, I already explained basically ILI or intelligent pigging, then excavation and visual inspection, or by applying various UT techniques or long range UT technique, MPI, automated UT, radiography, laser mapping. So these all techniques can be applied in the direct examination. When it goes to indirect examination, so there are like techniques like main purpose is not to excavate the pipeline, and only by the service movement by the technicians, we should be able to find the solution. Basically, benefit of non-intrusive or non-indirect is fast and non-intrusive, cover long pipeline lengths, used to prioritize excavation locations. Techniques, DCVG is a direct current voltage gradient. SIP survey is also like a pipe to soil potential to assess the CP effectiveness. ACVG is the same. It is the alternative current voltage gradient measurement. So this technique can be used. Then Pearson survey or current attenuation survey is also applicable. Then we can also use GPR and fiber optics, pipeline location support, and leak detections. Here, how to work together, external corrosion direct assessment ECDA, where ECDA is like a second technique which is called indirect inspection, which is part of like a ECDA approach. Here, this technique got four parts: pre-assessment, indirect assessment, sorry, indirect inspection or indirect assessment, then direct examination and post-assessment. So today, our main focus is on the indirect inspection, but unless and until we don't know, what is the problem which might be faced by the pipeline, and what is the diameter of the pipeline, what material of construction is, what service is there, what kind of coating is there, what kind of a CP system is applied, what problems are being faced on the route of the pipeline where ROW is being maintained, the third party threat and environmental issues are so. So pre-assessment very important. So pre-assessment is very important. And based on pre-assessment, we can select indirect inspection techniques, except direct techniques are also there, but direct inspection techniques are costly and practically may not be executable, or any reason, or operator may follow other alternative technique. This could be one of the alternative techniques. So direct examination means one ILI. Secondly, we can dig the bell hole and look at the pipeline by direct measurements. Post-assessment, once we have the result of indirect inspection and direct examination results, then we can calculate the integrity aspect of the pipeline, we can calculate future life of the pipeline, and we can make decisions for the repair and replacement as it would be applicable. So standards, which is normally governing standard overall is ISO 55001, which is asset integrity management system. Then for pipeline, gas pipeline, the standard is ASME B31.8S, which is managing system integrity of the gas pipeline. Then API 1160, which is managing system integrity for hazardous liquid pipelines. Then NACE SP 102, which inline inspection of the pipelines. Then NACE SP 104, the use of coupons for cathodic protection monitoring applications. Then stress corrosion cracking, direct assessment monitoring. Then NACE SP 0502, a pipeline external corrosion direct assessment, which is the main topic of today, ECDA, and indirect inspection is part of ECDA. Then NACE SP 0207, which is performance of closed interval potential survey and DC service potential gradient survey on the buried pipeline. Then pipeline external corrosion confirmatory direct assessment is also 02110. As just to get you familiar how this standard look like. So this is the ISO 55001 standard as asset management system requirements. Then there is a managing system integrity of the gas pipelines, ASME B31.8S. Then managing system integrity of the hazardous liquid pipelines, API 1160. This is the NACE standard. Basically, SP102. This is SP104, coupons for cathodic protection, use of coupon for cathodic protection monitoring applications. Then this is SP0204, which is stress corrosion cracking due to high temperature and temperature fluctuations. This is a very important standard. If at the downstream of gas pipelines, if air coolers are not installed, or if hot gas is being injected or being transported through the pipeline, then compliance with this standard is very, very critical. It's called SCC, direct assessment methodology. Then there is 502, which is pipeline external corrosion direct assessment methodology, SP207, then SP210. So these are the standards which we normally use for the direct or indirect assessment of the pipelines. So it's very important, we should know that all these activities, what we are doing, would be governed by the applicable standards, and it's not like anybody can do by their own way. If we have to do integrity assessment, then we can do properly by following these standards. So just to understand, what threats, dangers are applicable for the integrity of the pipeline. This is the first thing. Then if we know what the threats are, then we can assess them whether directly or indirectly. That is the subject of the webinar. Now, when we say indirect means without touching the pipeline, without excavation the pipeline, right? That is the basically indirect assessment. Here, basically in ASME B31.8S, section 2.2, 22 root causes are identified, where 21 threats are known, one is unknown. Unknown means it could be combination of all 21, or still we may not know the reason. So total 22 root causes, where 21 threats are grouped further in 9 categories, and one is unknown, which could be combination of 21. Okay. Now, what are these threads? First one is unknown, which could be combination of other. Then all these are divided into 9 categories where time dependent threads are there, like external corrosion. There could be any kind of external corrosion due to whether cracking, this is stress corrosion cracking is there, thinning is there, internal corrosion is there. Then resident or the manufacturing related defects. When, for example, when pipeline is being welded, so there could be a defective seams, there could be a defective welds, right? To me, manufacturing means when pipeline is being manufactured in the mill, when pipeline is being manufactured in the mill, it may have a problem with the defective seam. There could be some defective pipe or plate of the pipeline may have some problem. Whereas when pipeline is being welded in the field, it may have a defect in the weld. There could be RT may not be done properly. There could be some like a lack of fusion, lack of penetration. There could be some other issues like a subsurface crack also. So these are defects. If they are not repaired at welding stage, at fabrication stage, it may have a problem later on. Then there are equipments which are being used on the, for example, flanges. If there is a gasket, or if there is any further like a flange to flange connection, or there is a pump is being connected with the pipeline, or a compressor is connected, other equipments are connected. These equipments or these connections may have a problem. Those are required to be managed also. Then there are like random or time independent kind of threats, like a third party. If a third party or sabotage would be affecting the pipeline, then it cannot be like a controlled. This is also a threat. Then there are incorrect operational procedures, which is very important, like the pipeline is operated within the integrity operating windows and within operating limits, and the operating manuals and procedures are being followed by the trained operators. Then weather-related issues are also there, as I discussed earlier. Lightning may also cause problem for the pipeline integrity. So these are the 22 threats which are categorized in 9 categories. These are the 9 categories. Unknown is not listed here. Time dependent, stable, manufacturing related defects, welding and fabrication related defects, equipment related problems, third party related problems, incorrect operations, weather related and outside forces, interactive nature of the thread, which is basically unknown, which is the last one. Now, if we see the comparison, what is the contribution in the failure history, like the number of incidents which occurred over the years from 1985 to 2001, if this is a graph, like how many incidents occurs due to third party damage, which is the highest one. Then external corrosion caused the second highest, internal corrosion third highest, natural forces fourth highest, and then similarly other factors which cause the failure of the pipelines. Like as per UK OPA pipeline product loss incident and fault report from 1962 to 2016, if you see that 107 incident occurred due to corrosion, whereas 96 incident occurs 22% due to pipeline weld material failures, and similarly equipment failure has caused 75 incidents. Similarly, if you say the liquid pipelines here, so 24% incident due to pipe weld in material failure. Then there are natural forces damage, right? And 52 incident, 22%, which is excavation damage or corrosion is the third one, 43, 18%. So these data indicate that if we cover the issues related to fabrication related controls, excavation related controls, like a third party excavating their pipeline, they're damaging the pipeline, or corrosion related issues, or preventive related issues, or equipment failure related issues, if area by area we focus, then these incidents can be prevented. Like if we see external corrosion, internal corrosion, SEC, in general, today's topic is not related to corrosion, but since we have to do indirect assessment, we have to understand what issue we want to detect through an indirect inspection technique. This is the external corrosion, internal corrosion, SCC. This is the first item out of 22 threats. Here, external corrosion, we know that there could be a corrosion due to soil, there could be corrosion due to water, there could be due to SRBs, and how we try to find those basically external corrosion issues. So there is a specific mechanism, and then accordingly we can find that. So here, NACE 502 ECD technique for non-piggable pipeline can be used. Also, there's a direct assessment NACE SP201 ECDA. ECCDA for piggable pipeline can be used. Similarly, ILI can also help to find these defects. Then internal. External are due to environmental side, whether external rain, external water, external soil, or there could be like a weather-related issues. Whereas internal is due to process conditions, the damage mechanism which could be caused by the internal fluid, which would be handled by the pipeline. So that like if we have a material compatibility with the service, if we are maintaining the like integrity operating windows or composition of the fluid, or for example, if a pipeline is designed to handle gas, dry gas, and water quantity should not increase more than 7 pound per million cubic feet. So then in that scenario, so there would not be any internal corrosion problem. But if the upstream glycol dehydration unit or gas drying unit is ineffective, then if water is gone with the pipeline, then corrosion can be increased. So that part, it means if we need to monitor that. Similarly, if there is a hydrocarbon like a finished products which are transported by the pipeline. So in those pipelines, if there are intermittent flows, this process water, if that is separated out in the bottom of the pipeline, that could be very corrosive. So those issues would be still there. But in general, if we maintain the conditions of the fluid, which would be managed by the pipeline, then these internal corrosion issues can be minimized. Stress corrosion cracking, which is very like a threatening situation. Like we have seen many incidents due to SCC in the pipeline. If the pipeline is handling high temperature gas, and if the due to fluctuation of the temperature, it may cause like accumulated salt deposition. Number two, if the temperature is high and then coming lower, the coating of the pipeline, like when pipeline expand due to high temperature, the coating will also expand. But if the pipeline is like temperature is dropping, then steel would contract with coating which is made of non-metallic material, epoxy or 3-layer polyethylene, that will not contract. So this would disbond from the pipeline. If the coating disbond from the pipeline due to high temperature expansion and then contraction, then pipeline would not be protected by the like a coating, and the CP would be ineffective. And in that scenario, if water and soil keep accumulating over the surface of the pipeline, then this can cause SCC and external failure. So there are incidents where pipeline fail. So nowadays, it is very like a common practice to maintain temperature for the inlet fluid of the pipelines. Then like manufacturing related defects, just getting you familiar, there are like pipe seam defects and then pipe related defects which has to be taken care. And these defects are seem like if this is a weld seam problem, and this could be a pipeline quality problem where pits is there. Sometimes there is a like subsurface lamination issues. So these defects has to be taken care. Next, manufacturing related defects also are covered when we are buying the pipeline in the earlier phase, right? All the quality issues, whether plate, rolling, weld seam, or whether seamless weld. So these quality issues are required to be managed when we are procuring the pipe before seemed like a joint field joints are being managed or made. Welding and like welding is a main important, whether whatever welding procedure to be applied, whether is a welding would be done by the qualified welder or by machines, the WPS has to be qualified. Then the same has to be applied with a caution. There should be intermediate inspections followed by the RT or other AUT inspections by the UT at these techniques. And if there is any defect found, this defect has to be corrected and then repaired and then redo that inspection. Then accordingly, these defects can be controlled. Then all the equipment which are being attached with the pipeline or which are the part and parcel of the pipeline network has to be designed in accordance with international applicable codes and standards, and their connections, their flange joints, and their behavior in terms of vibration, in terms of quality has to be managed. Third party damage, like, so this has to be controlled, like all the areas right of the way to be managed. Third party interference has to be prevented or managed. So this is the important aspect. So these are like a fabrication related, just to see the issues what are shown here. There's the pipeline related defects, which normally become part and parcel of the pipeline issue. Defective fabrication, like if there are defects like underfilled, undercut, poor penetration, lack of fusion, spatter, porosity, overlap, inclusions, excess reinforcement, cracks, and burn through. These are all defects, and this should be managed through the welding controlled WPS activities. Then here Welding and fabrication again, wrinkle, bend or buckling, stripped thread, broken pipe, coupling failures, these are also part of the pipeline welding and fabrication activities in the beginning. Here, we had equipment related issues. For example, this is the flange connection where gasket and the corrosion, you can see the issues. Similarly, control and relief equipment on the valves, the PSVs, those can have a problem. Pump and package failures could be a problem. Gaskets and control and relief pump related issues which are required to be managed. Third party, like if the pipeline is, we have a pipeline, another third party is coming in nearby. So third party, like here, if you see, this is our pipeline, and this is the third party pipeline which go just below this. So this party can damage this pipeline. So we have to see the third party would not be damaging the existing pipeline. Previously damaged pipes such as dent and gouges, delayed failure modes, and it can have a problem. Vandalism or the terrorism, that is out of control. This has to be managed at state level or government level. Incorrect operation, like we discussed earlier, incorrect operation means like the operator will not be able to manage the pipe in proper order. For example, if a corrosion inhibition is to be managed in the pipeline, and if due to procurement issue, if corrosion inhibitor was not available or chemical was not available and operation did not make a noise and they operated the pipeline without that inhibition for a certain period, so it would impact the integrity. Similarly, if the pipeline is supposed to handle dry gas, then water dehydration unit or glycol dehydration unit has to work properly at upstream of the pipeline. Weather related, see, as we said earlier, so there's no unexpected, like there could be a worse scenario which people may not expect. Otherwise, we have a last 100, 200 years history. If any pipeline is being designed in that particular area, the weather related, lightning related, heavy rain or flood related, earth movement related data should be there, and pipeline to be designed and constructed to take care of those issues. If anything comes beyond the previous trend, then there could be a surprise for the owner. Otherwise, we cannot make a 3,000 kilometer or 2,000 kilometer pipeline from one country to other part of the region and without knowing the area, and then next 6 months later the pipeline is damaged by the weather and we cannot transport the gas or oil or water in the area where we want to transport. Then unknown part, this is excessive hot and cold weather issue. Then lightning, see, we know that if lightning can occur any place, we have to have a earthing of the pipeline, so lightning is not impacting the pipeline itself. Heavy rain and floods we can manage. Earth, like us, if the pipeline is undersea, so we know that last 100 years behavior of the sea, we can design our pipeline to withstand those currents, waves, and whatever surprises may come underwater. So geotechnical, practically we know. Otherwise, if the stress analysis, the design aspects, those are required to be managed. These are being managed anyway. In summary, there are 9 categories. Each category is paid attention. And in our part, where we are focusing mainly is a time-dependent external corrosion, internal corrosion, SCC related, and what kind of direct or indirect techniques are there, we have to follow that. Otherwise, if you see these manufacturing related defects or welding related defects or equipment related problems, these 3 are the past when pipeline was designed and constructed. So at that time, the project team should have taken care of these issues. If there are some certain problem unresolved as a punch list, that should be given to the operators. If that has been given, then operating company can take care of it. However, if those are hidden somewhere, then there would be problem. Similarly, like when we say third party, so third party has to be managed by the proper management of the issues. Like who are the third parties, who can cause that problem, then accordingly pipeline can be managed. Incorrect operation, as I said earlier, is a part and parcel of the operational team responsibility. Weather related and outside forces, those should be forecast. Otherwise, we cannot. Like I know in one project where the soil settlement damaged the pipeline in Malaysia and operation was delayed for 1 year. This can happen. But if we are aware of the issues, then a route of the pipeline should be taken away from the area. Even the length could be increased a little bit. Why? Because you are bypassing that particular defect, like a dangerous area. It should be done. If you take a certain like a risk, then there could be a problem. So just to check if all of you are participating in the discussion. So there is a question for all of you to answer. Please try to pick your answer. Next slide would be the answer. So here threads are grouped into dash of related failure types, categories like how many categories? Type of failure according to the nature and growth characteristic and further delineated by 3 time related defect types. So many people are answering this. So whether answer is A, B, C, or D, right? Please try to pick your answer. So here mixed answer coming. These are not 6 categories. Looks like these are basically answer is C, mostly right now. But there's somebody pick A also. So it's C, 9 categories. 8, if I go to my previous slide, 8 are there in this table and ninth one is unknown. Next question. Mechanical threat is discussed in Dent's defect, Gauge's defects, combined dent and Gauge's defects, all of above. So mechanical defects of the pipeline are covered under which of these items? Please pick the answer. Again here, mostly right, but one party also picked A. So it's basically Gauge's and dents both are part of the mechanical defects. The answer is D. Thank you. So this was the just check if you are participating in the discussion. Now there is a subject, why metal corrode? How corrosion take place? Why corrosion take place? Just like a metal, like kullo nafsan zaikatul maut. We have Arabic statement in Quran, like kullo nafsan zaikatul maut. I mean everybody who comes on this earth has to die. Same as all the metals which are used in any of the process side, those metals would be corroded, because in general, when we produce metal like iron ores generally exist in the form of iron oxide. We heat it up, we put in energy, and then we produce iron. And that iron is used either in the iron combination as a steel or iron itself. And when this iron would be used in production, like for any pipeline or any equipment to manage any fluid, so it would have a tendency to revert back to iron oxide. This is normal tendency unless until we prevent it. So all the metals have tendency to react with their environment to revert to its natural and more stable form called oxides, rust and corrosion. Here, in general, iron oxide, when we taken over from the ores, in the blast furnace we heat it up, then we simmer and again further heat it up, and then we get the steel, and this steel go to pipe mill, and pipe mill make the equipment, steel pipe, and this steel pipe we use to transport fluid, and we make equipments, and those equipments have a tendency to get corroded again and turn back to iron oxide, just like a nitrogen cycle. This is just a process. If you can see it, pipe is made. So again, why corrode? Basically, if you see here, steel, Fe plus carbon, corrosion process, Fe energy released, it made iron ore or rust. In the iron rust, energy added, Fe made, Fe plus C, steel is made. And this process keep going. So these are the steps we normally occur. Why metal corrode? Metal, just to remember for a layman or for the young engineers, because steel is produced from iron ore by putting in energy, and then we make the equipment. When equipment is going to use, it can absorb energy and get corroded and then release the energy. So this is the normal equation, like it need electrolyte hydrolysis process, like Fe, if we know that like all the metals, whether if you remember in the chemistry, in the periodic table, we have group 1 and 2. Like a sodium is group 1, Fe is group 2, and similarly we have a group 6 and 7 in the periodic table on the other side of the periodic table. On the left side, there are 1 or 2 electrons in the last orbit, whereas in the right side, whereas chlorine, whereas the bromine, or these sides or oxygen. So these elements are having 6 or 7 electron in the last basically orbit. So metal would like to lose those electrons to the group 6 and 7 of the periodic table, and this way this bond is made. If you see this, Fe combined with oxygen with the presence of water as electrolyte, there is intermediate process of the water, and it converts into Fe2O3, and this is the basically ore, and this is the oxide form of the steel. This is the corrosion process. That's why this corrosion take place. This is a basic chemistry, and we need to remember that. Similarly, if you see, different metals have different tendency of oxidation. The best material is gold, which does not corrode as such. That's why it is the most costly metal on the earth than platinum. If you see this, magnesium, aluminum, zinc, I don't see sodium here, but sodium is also one of the metal which also get corroded very fast. It does not stay alone. But anyway, magnesium here, electromotive force, series of for metals, rank metal according to their tendency to corrode. The magnesium got highest tendency and gold got the lowest. Iron is the fourth in the basically row. This is also got tendency. So this EMF value can tell us what is the tendency of the metal to get corroded. If we mix up and we make a like a stainless steel, it is a mixture of various metals, and then it have a lesser corrosive capability. This is how you make the combination of the metals to produce more resistive CRA, corrosion resistive basically alloy. So why metal corrode? That is the basically normal process, as we said earlier. If all the metals they have a tendency to go back to the ore kind of situation. In ore, normally we take the example of ferrous or ferric. Ferrous means steel, iron. They stay as a Fe2O3, and by heating it up or by giving energy, we try to generate Fe, and by combining with carbon or some other compounds, other elements, we try to make it like carbon steel or steel. So this is the process. So these metals have a tendency to go back to the. So in general, as I explained earlier, all the metals belong to first and second group of the periodic table. And in that periodic table, for example, they have a tendency to lose. In the group 1, basically elements can lose 1 electron and 2 can lose 2. And similarly, group 6 and 7 on the periodic table on the right side. Again, the issue is what these reactions take place in the presence of some electrolyte. In general, it is aqueous situation or water presence, right? Sometimes some reactions does take place without water as well. So now, as we see this oxidation process, so the metal which is part of basically as a periodic table row or column 1 and 2, and then there are the elements in the column 7 and 6 in the periodic table. So both one group of elements have a tendency to get cathode. So the anodic and cathodic reaction. So anodic and cathodic reaction which take place, the loser is called anode and it got depleted. And that's why we have to prevent that. Now here, dry cell, like if we see this process of electrolysis, where we have a dry cell analogy, carbon graphite electrode is there, then voltage is applied, then electrolyte is provided as a solution in water, or ammonium chloride solution could be there, zinc electrodes could be there, then electrical contact between electrode is there via wire. This we can see in the outside part where current can flow, can see, and in this process one part is losing the electron, other one is taking the electron. We can see it, right? So oxygen concentration cell also, in the same metal, there could be one cathode, one anode, then electron is being lost via electrolyte. Like little or no oxygen is required. Right? Okay, that's fine. Thank you. So we are back to normal. So I'm told by my technical team. So here, this is the process how this corrosion take place. Now, anode, cathode, and oxidation reduction reaction goes on. That is basically a corrosion mechanism. Sorry, I lost a little bit concentration. I hope it will not be distracting you. Similarly, like we have a cathode anode, like a compression station, hot gas comes in, current flows from this electrolyte, anode to hot to cold. This can also cause heavy corrosion. This is also one of the process of the oxidation. So I try to cover why corrosion take place. It is the oxidation reduction process, which goes like when we produce steel or iron was in the oxidized form. We deoxidized and produced Fe and then mixed with carbon or other components and made the steel and use it. And if there's tendency to go back to as a ore form, because it's a natural form of the steel, so it can go back. So where does corrosion occur in the metal surface? General. Like whether it would be at anodic part, whether it would be on the cathodic part. And we should remember the metals which belong to periodic table 1 and 2, they are donor of the electron, they are called anodes. And the oxygen and chlorine or these which combine with metals, they are called cathodes generally. One time oxidation taking place, other time reduction taking place. So please try to answer this question. The substance is called what? Please try to fill the answer. Mostly right. It is A. So we covered second part of the presentation, like where general knowledge, then type of threads, then why corrosion take place, and the next one more question. Why does the bottom of buried pipeline often corrode faster than the top? There's a question. Why does the bottom of a buried pipeline often corrode faster than the top? Maybe this discussion we left in between when there was a discontinuity of the presentation. So here, please try to fill the answer. Mostly right. The bottom of buried pipeline corrodes faster because it is often with less oxygen and anode compared to the top as a cathode. The answer is C. Just to get you involved, this is why these questions are added in the exercise. Now, overview, like we have to go to next, because just like you may say that we are having a lot of debate, but we are not going to indirect inspection yet. But basically, we are trying to understand why corrosion is taking place, then how it can be prevented. We will see that coating, CP. Then if we still corrosion taking place, how we have to find out. See, the corrosion in the pipeline would occur if coating will fail. Corrosion in pipeline will occur if cathodic protection will fail. Or corrosion in pipeline would occur if provided and bare steel is buried in the soil, it will corrode very fast. Because, as I said, kullu nafsin zaiqatul maut. Like every like a steel pipe goes back to their ore form, Fe2O3. It is natural tendency, like if there is a fuel, it will burn and go back to CO2 because of natural occurrence. Right. So overview of cathodic protection is working principle a little bit. We will spend a few minutes on this. Here, for example, there are two methods which are protection. One is sacrificial or galvanic anode, and second is impressed current. Sacrificial or galvanic mean we have attached with the pipe, we attach with the steel. It is a sacrificial, means the anode will sacrifice itself, but prevent corrosion on the steel. That is the phenomena. So sacrificial or galvanic anode of CP system relies on the user which will lose itself, made of material that is less noble compared to structure to be protected. Second one, impressed current, mean we provide the electrons via live power, like via this AC current by TR unit, transformer rectifier, and then we have an anode there, and this anode provide electrons to the cathode, which is the metal. So we try to make pipe as a cathode and try to produce anode outside, and which gets electron directly from the power, and it will prevent corrosion on the pipeline. So there are two techniques. One is sacrificial, where anode provides the electrons which would be lost by the pipe. It would be compensated by the sacrificial anode. Similarly, in the impressed current, where we have a direct link over the power, any electron would be lost by the pipe, would be our structure would be compensated by the power in the same ratio. In this way, corrosion will not take place on the pipe, the pipeline. Similarly, if you see this, sacrificial is a small galvanic anode CP system is recommended for small isolated structures, whereas ICCP, impressed current CP system, is like you are lightening the full plat like a stadium by the lights. So here means whole pipeline could be like a 20 kilometer to 50 kilometer pipeline can be protected by one TR unit. Then we have to remember in the term ASME. A mean anode, which could be magnesium, aluminum, or zinc. C mean cathode, metal structure to be protected, underground piping or underground pipelines. So like a CP system only works either underground or in the water. It cannot work for above ground. Yes, CP system can work like a corrosion inside the like a tank bottom. There could be sacrificial anode which could be attached with the bottom of the tank. Sometimes it can be used inside the separator. But CP system cannot prevent corrosion outside or if there is no electrolyte. So for CP system, we have to have electrolyte, which is item E, electrolyte. The anode and cathode should be buried in electrically conductive soil or water. Then CP system can work. That's why everywhere we are not talking about CP. There somewhere we have to use CRA material, corrosion resistance material. Sometimes if the normal material may not defend corrosion or prevent corrosion, we go to GRE material, or we go Inconel 825, 625, ST300. So all these materials, what we use, the main objective is how to prevent corrosion. So this is a, remember, in the cathodic, in the cathodic current, we have to remember ACME, anode, cathode, metal connected through the electric cable, that is called metal. Then E means electrolyte should be there. Here, like if you see a CP transform rectifier, if you see first thing, we have a junction box. Here, I forgot to explain this. CP junction box is added in the current to monitor the current flow from anode to structure and to assess whether the anode is functional or not. Here. So here we have the anodes, sacrificing anodes. Next part, same. We have this TR unit, and all these anodes are directly connected with the junction box, and junction box is getting the power directly from the power supply. So this can provide current directly, and it does not have a threat. If what happens in sacrificial anode, which are mostly provided in the subsea pipelines, so we have to see what the depletion rate of these sacrificial anodes. Like subsea structures, we see that the sacrificial anode get depleted and we have to retrofit again new anodes. So whereas in the ICCP, we don't have that problem in general. So, but we need to maintain power supply, TR unit functionality, whether it is solar power or the power being provided by the grid. So this will help to maintain CP system. And what the use of CP system, as we studied earlier, the metal normally corrode because it acts like an anode. But by applying CP system, we try to make pipe as a cathode, and we make an artificial anode which is compensating the loss of those electrons which could be lost by the metal. See, cathodic protection is achieved when the potential of all cathode sites reach the open circuit potential of most active anode site. Corrosion on the structure is eliminated. Moreover, cathodic protection is a technique to reduce the corrosion of a metal surface by making this surface as a cathode of an electrochemical cell. So now if we see that the advantage or limitation, as I said earlier also, sacrificial anode is easy to install, but it got a limited life. Whenever a node would be consumed, we have to install new. So that's the only issue. Low maintenance, low cost, but life is limited. This is the point. Whereas when we go to ICCP, higher equipment and installation cost, higher maintenance cost, possible interference problem with the foreign structures, frequent monitoring is required, but greater driving voltage, higher current output, adjustable current output, constant current can be maintained, and it is not life would not be lost sharply. So, question to get you involved: how CP system works? By increasing soil temperature around the pipe, by coating the pipe at the top, or by making a metal structure, the cathode, in an electrochemical cell, preventing it from corroding by force it to receive electrons. Then last one, by increasing mechanical stress, so crack close. So answer mostly right. The answer is C, by making pipe as a cathode, which is naturally act like an anode. This has to be remembered. So now other part, like I was saying, when we have a pipe for external corrosion, so we got two protections, like rather three. One is the nature of the steel, carbon steel. Number two, we can have a coating. Number three, proper coating, joint coating. And then there is a CP system. So CP system cannot be an alternative to the coating system. Without coating system, we need to provide too much electrons to the metal, which we cannot provide. So corrosion will take place. So CP system works in combination of protective coating, because the protective coating prevent the connection between soil and the metal, and the electric path is broken generally, and corrosion does not take place. So without CP system, coating system can also prevent corrosion. So here, coating provide a physical barrier between the metal and the electrolyte. This decreases the amount of water and oxygen or hydrogen ion that diffuse to metal surface. The coating also places an electrical resistance in the current circuit, if you can see it here. So here, current flow, coating, anode is there, cathode is there, but there is a barrier in between both. So coating holiday, when there could be a damage or there could be a defect in the coating. The holiday is a discontinuity in the coating film. For example, there could be a pinhole, this could be a disbonding, this could be damaged by some mechanical hammer. Discontinuity can be void crack, the thin spot, foreign inclusion, or any contamination which will lower the dielectric strength of the coating system. A pinhole is a small pore-like flaw which, when extended entirely through the film, representing a discontinuity. Mean if the coating is damaged, then there could be a corrosion, because that would be the path between the metal and the surface outside. Metal is anode, outside is a cathode. Electron can go outside, which will cause the corrosion. So defect related to buried pipeline. So means what? If we need to prevent corrosion, we need to have a good coating. If coating got a defect, we need to assess it and repair it. So for that reason, we should know that what are the type of the defects for the coating system. For example, how coating system is applied. First, we prepare the surface of the metal by rubbing it, and like SA2.5 level. Then there is a primer coat, there is an intermediate coat, then there is a final coat. The thickness, DFT of the primer, DFT of the second coat, DFT of the third coat, and then dry time, environment, weather, rainy season, and so and so. So those all aspects are taken care by applying right coating. If coating is applied rightly, then supported by CP, pipeline would not have certain external corrosion issues. We are not, SCC is taken out. We are not saying the pipeline is operating at high temperature. If pipeline is operating within the allowed temperature range, then coating is good quality, CP provided is guaranteed, there would not be any problem for the pipeline externally. However, we should know what kind of defects could be there in this process. So what defect is? First, surface preparation, then primer coat, intermediate coat, final coat. If there would be any problem in this coat, quality would be compromised, or dry time would not be prepared, or surface would not be prepared properly. So there could be certain problem, or quality of the paint may not be right one. So here, what are the type of defects? Lack of surface preparation at initial stage, excessive damage to the primer, time lapse of the coating application, lack of adhesive, primer to first layer, compatibility of pipeline and grease weld joint coating, improper application of the field joint coating, wrinkling and bagging, blistering, cracking, disbonding coating. So these are all defects we should know. And if these defects would be there, pipeline would be corroded externally, and there would be problem, and you have to install new pipe, it would be corroded. So generally, there are three type of coats. As I said, generally it could be 4 or 5, like maybe the layer also. But there are three: primer coat, intermediate coat, and top coat, as we said earlier. And before that, surface preparation to SA 2.5, as per the standard, and dry time, quality, and quality of the coating, and then the painter qualification as well. If the painter would not be qualified, he may put all the paint at one side, and then there would not be proper drying. So what are the normal coating types? Simple one is asphalt, bitumen, enamel. This was the old one. So it can work 10 to 15 years. Then second one is fusion bonded epoxy coating. This is the second easy one, and it can last up to 25 years. Then temperature wise, when it is 90 degrees Celsius, I don't believe in. Coating system, in my view, in general, does not work more than 60 degrees Celsius. If a paint supplier is saying my coating can work up to more than 60 degrees Celsius, there's a problem, because as I explained earlier, in the temperature cannot be guaranteed it will stay as we define, because if temperature is like a varying between summer to winter, like it may go up to maximum 90 and then come back to 25. So when temperature increase from 25 degrees Celsius to, let's say, 90 degrees Celsius, pipeline would expand. If pipeline will expand, the coating would also expand. When temperature comes down, then steel can contract, but non-metallic, this coating will not contract. It means it will break the bond between pipeline and coating will break. And if if the coating is disbonded, the pipeline would be considered not protected. And that's why in high temperature lines, CP system is unable to protect. Coating system is unable to protect those lines. And that's why the high temperature operation of the pipeline is always, subsurface pipelines is always like discouraged. So they always recommended there should be temperature control before fluid goes into like underground pipelines. So here the 3-layer polyethylene is one of the best coating nowadays. It is being used. And then shrinkable, like a heat shrinkable sleeve, those are used at the field joints. So we should know these are general coatings. Now, one question to make you awake, because otherwise I'm speaking and you people may not be interactive. So here question is, as gentlemen and ladies, we will have a question answer session, one in the middle and one at the end also. So today I'm going late. So maybe we'll have a one question answer at the end only. So now I'm presenting a case where we have done a DCVG and CIP survey for a cross-country pipeline in a African country. So this pipeline had three sections. Section A, 25 kilometers, section B, 350 kilometers, section C, 480 kilometers. This pipeline was constructed in 2006 with three-layer polyethylene coating and HSS sleeves were also used. Impressed current is provided for this pipeline. And however, the same has not been maintained. CP system was not maintained properly. We, like a scope work, coating fault identification, defect sizing and location, risk ranking, selection of bell holes, excavation to validate the DCVG results, which is when we say bell hole to validate DCVG, that is basically direct examination. So it was a combination of indirect and direct examination. Then coating and pipeline integrity assessment and recommendations. Similarly, the CIP survey, CIP, which is a basically potential survey for the CP system, the complete protection profile of the pipeline at 1 to 2 meters interval, protection status according to criteria, unprotected, partially protected, and protected, identify interference areas, correlating protection with coating condition, coating fault, yes, no. Then CP data analysis, reason for no or low protection. Then recommendation were supposed to be produced. Then bell hole inspection, all the defective areas where we suspect there is a coating is not effective or the system is low protected. So record geo reference coordinates, evaluate coating condition, bond with pipe, blister disbondment etc, mapping of the corrosion defects under the coating, pipe to soil potential, reading at upstream and downstream of the dig site, soil resistivity test for the earth fill surrounding the pipeline at dig site. Soil constituents analysis like pH, chloride, sulfate, sulfide, and biocarbonates. Pipe surface assessment, photographic documentation. This was also part of the scope. Now, external corrosion depth assessment, like this is a part of the process. I just want to quickly go through because time-wise I would be fast. Pre-assessment I explained earlier, like collecting of the engineering data, operational data, historical data, and the soil, environmental, and see what can go wrong. What can go wrong? Then, knowing that, we go for indirect inspections. Like we went for DCVG CIP survey and also the bell holes. Bell holes is a direct assessment. After doing DCVG and CIP survey, we go for direct examination. After direct examination, now we know the health of the pipeline. We know the condition of the coating. We know the weak points. Then post-assessment, like if the defects were there, what is the nature of those defects, whether those are acceptable, what kind of repairs are required. So these are the 4 stages. So here our main focus is indirect inspection, but we did on this particular project direct examination also, we also performed post-assessment as well. So pre-assessment in general, like what we need to get the information, pipe-related information, construction-related information, soil related information, corrosion control related information, and operation related information. All this information which list 44 data elements which are considered in pre-assessment. So I explained earlier, so we gather all that information. Then what region? So we try to divide the pipeline in various sections or regions. Means above ground portion, underground portion. Underground means marshy area, dry area, hilly area, any river crossing area, any railway crossing area, all those regions. And then the similar metals, similar environment, or there could be a external environment might be changing. So then accordingly, we applied indirect inspections applicable to those regions. Like here, normal ECDA region contact like soil contact, like a contact area, paved area, bodies of water, subka soil, low water table, then also pipeline crossing under high voltage AC current, pipe wall thickness as it might be changing, isolation, electrical earthing, compressor station separately, CP system operations, regions protected with sacrificial node. If there are some portion, those were also specified separately. And this way, these are the like basically regional classifications from CPF, then pump, and then another CPF and pump, and then there would be a heater and pump, then heater of the oil and pump because it got wax in the oil and it needs some heating also. So this way, these are the sections of the pipeline which were made as a part of this project. Then, like where like we need to have a CIP survey, where we need to have a DCVG survey, Pearson survey, or current attenuation survey. Those were basically identified as a theory point of view. Now I have to cross this. Here, like a combination, this is a combination, like a CIP survey or CIS survey. CIP survey is showing where the pipeline is having like a CP potential above 850 minus 850 millivolts or less or far less or more. And then DCVG will be showing the defects where our pinhole or the defect, what kind of defect is there in the basically the coating. So then indirect inspection, what we carried out, like close interval potential CIP survey, as I said earlier. Then we carried out DCVG survey. Then we also carried out ACVG survey in certain locations. And then basically the evaluated categories coating conditions. Then soil resistivity also checked on the bell holes locations. So these two things what we are showing here today, CIP survey and DCVG survey result. So now here there are basically CIP survey, DCVG, ACM, and ACC all got strength and weakness, but like the better combination is CIP and DCVG, which are used basically. So time-wise, I cannot go through these details, but there is a weakness and strength. CP is only CIP surveys to see where the pipeline is. CP-wise, we are able to maintain required potential or not. DCVG basically able to identify all type of defects, whereas PCM, ACVG, they also help to define the defect, but in the difficult areas, it may help better. Now, like how we carry out close like interval CIP survey and DCVG survey, which are carried out side by side. If you see, first thing we try to locate the pipeline and GPS position. This is the first person. Then we have a person who throw little water. Then DCVG, and last person is moving with the CIP surveys. So this is not easy walk. You have to, if like African country, if you are moving from one part of the country other part, you have to walk the pipeline kilometer by kilometer or meter by meter. Then the survey result, like this is the DCVG, location of the pipeline, detection of the cable fault, delineation of the coating defects, behavior of the coating defect, severity and nature of the coating defect, stray current interference, checking of the insulating flanges. So strength we have already discussed, it can help to find all the defects. Then this is how it works. Principle of operation, like if there is any, like it create EMF or voltage gradient across the pipeline. If a pipeline is fully coated, then the EMF or the gradient would be lesser. But if there would be any discontinuity, then there would be more current flow from the basically pipe to the outside surface, and we can catch that there is a defect. When DC signal is applied to a pipeline, current flow through the soil towards coating defect generate a voltage gradient. If defect, more gradient, and less defect, less gradient or no gradient. And this way we would be able to find the defect. Just like the same, If there is a defect, there would be a gradient, and we can see here is a problem on the pipeline. Similarly, as we are walking through, reading are usually taken 1 meter apart. Always have a both half cell on the ground when recording the voltage gradient. Preferably, the pipe located should be just ahead of the DCVG as we showed earlier, surveyor to allow him to walk over the pipeline route. Then this way, the pipeline, there is a first person is the who is locating the pipeline, then DCVG and log, and then SIP was going there. But if these three people, like this is the like a position here, there is a analog DCVG instrument where center point is there, and here is showing defect gradient is this side, here showing gradient is this side. This is the position where highest gradient is there. So DCVG defect identification, well coated pipeline exhibit high pipe to ground resistance, and no or little current will flow to these sections, and there will be effectively no measurable voltage gradient. Whereas if defect would be there, there will be more flow and gradient can be identified. Similarly, the nature of the DCVG result, as I explained earlier. Now, if you see this, no needle movement, needle to deflection point, where the defect is back and forth, and this way you will be able to find the defect. And with the location of the coating defect, equipment lines are there, no signal when directly above the defect, no signal, no needle deflection when you're exactly on the defect. But when you are before defect, signal goes this way, and if you're going forward, it will go other side. This is very important if you want to understand the DCVG survey technique understanding point of view. Here, coating defect identification, once identified, we know that it is a defect. Then accordingly, we see how much gradient is there. That gradient will tell on the amperage wise or voltage wise where it is coming there. So here, having located in one direction, turn through 90 degrees and repeat the epicenter location. Then you will find here the defect and what is the gradient value. With the gradient value, you would be able to whether the minor defect, medium defect, or severe defect. Searching for the pulse, checking frequency at 90 degrees to keep the top of the pipeline. This is generally a 4-step search phase. Then coating fault is located as indicated by the change in the direction of the pulse. Here, see if this is a pipe, one defect red, other defect. Here, defect epicenter, other defect epicenter. Otherwise, no defect, it will be showing the location by this arrow. Here, where the two null marks cross the epicenter of the coating defect, this is directly above the coating defect, basically. Now, once defect is located, one determines it's important by measuring the potential lost from the defect epicenter to remote earth. So here, how we fill the DCVG meter range, current interrupter setting. So we try to fill like a defect reference identifier, then coating coordinate easting, coordinate northing, then defect chainage, and then upstream TC chainage, downstream TS chainage, and then these values and the percentage IR will tell what the nature of the defect. Here, if you can see this, percentage IR is like what is the value and what the total potential value. And then this difference will give like a severity of the coating defect, IR percentage, over the line to remote earth potential, on potential reading at the defect, instant of potential at the defect. So here, if we see, if for example, this is the IR percentage at 5000 ohm centimeter coating fault severity, 0 to 15 low, 16 to 34 medium, and 35% is high. Like a corrective action plan, no repair at low, consider repair 2 to 3 years, and then consider early repair 1 year at least, which is the high potential where coating defects are there. Otherwise, pipe will go in corrosion mode. Here, coating defect ranking at the region wise. These are how these defects are shown. And actually, if you see that we got 10 defects in section B, 1 defect in section A, and no defect in high category. Whereas like a medium were there, 1 in basically section A, basically 56 in section B, and 0.2 in section C. How they are shown, you can see this is the highest one, then yellow one is the medium one, and green one and 144. So these are the defects along with the pipeline, and this is the beauty of DCVG. You can see that. Now, just one question, like to get you involved. How does the defect in coating of pipeline is detected by DCVG? By measuring pipe temperature change, by checking the pipe color and paint quality, by measuring electrical voltage gradient that occurs when current flows into bare metal at a fault, by measuring the water level around the pipeline. The answer, everyone is right. B. Just to make you aware, like a DCVG is a direct current, uh, basically voltage gradient. VG, DCVG, direct current voltage gradient. This is the DCVG. Then DCVG is a dash assessment technique. Direct, indirect, proportional, accurate. Mostly answer is right. This is indirect technique. So I'm getting faster. Now we go to the last part, which is a closed interval potential SIP survey. The SIP data logger is a digital voltmeter with the built-in feature to read, report, remember, recall the on-off potential field data. One difference between SIP and DCVG, DCVG every record is kept by manual. There is no record kept by electronic because we are going on the pipeline route. Wherever there's a high value of voltage gradient, we know there is a defect. And then with the pipe tracker, we say this defective location is here. And then we send for random location to see whether there was a real defect. Whereas SIP survey, if we are taking, you can check where the potential is high or low. Here, level 1 TRU monitoring can be done. TRU monitoring, like a level 2 could be TRU in transformer rectifier unit monitoring. Then PSP surveys with potential, like a surveys of the CP. And then level 3 could be TRU monitoring, PSP surveys, and DCVG survey to be followed. Then we can have a 70% confidence. But if we have combination of TRU monitoring, PSP surveys, DCVG surveys, then SIP surveys, then we can have 100% confidence, like we have a better understanding of the pipeline. Here, intensive potential measurement at short interval of 1 to 2 meter along the pipeline, entire pipeline length. SIP identify area of unacceptable high or low potential caused, for example, by interference from other structures, coating damage, or current drain to the foreign objects. Here, like a test station is there, mobile data logger is there, and then we keep saying how the, like a, where the pipeline is having minus 850 millivolt above or low or very low. And it can be done both in the with the this CP system on or CP system off. Both conditions and data can be or the potential survey can be done. Like what is the potential between the pipeline and soil in terms of like if there would be CP working or CP not working. So this is the case where the values of the CP system changing across the pipeline route. There is another area where the numbers wise, somewhere number is more, somewhere number is less. There are on reading, there's off reading. And this is the 850 millivolt. If you see this 850 millivolt, mostly the current is on the above and a very high potential, like a more than required. And somewhere is less. Here is another one. So now, if you see the low potential, it should like a low fault category low. The values remain between minus 850 to 950 millivolt. Medium between minus 650 to 850 voltage. High less than minus 650 millivolt. The on-off readings, and then also if you see on and off gradient with 50 meter spacing, millivolt 50 per spacing, this range is there, which we need to follow. Here, CP system, like a strength point of view, the profile of the potential protection level over the pipeline. Then interference current, if not interrupted in the synchronization, may distort the accuracy of the results. Then interconnected parallel pipeline accumulated potential may mask the defect. Here, limitation, efficient method may cover 5 kilometers per day, accurate plus minus 1 meter, entire pipeline is walked, enabling inspection of CP installation and ROW condition, identify unprotected points and other non-stable potential conditions. Here, if you see that, like a disbonded coating, for example, all coating assessment techniques are sensitive and field conditions, right? And none of survey works if the pipeline coating is disbonded. Like this is a high temperature service issue. So the question is, there is a qualification. If the pipeline, the coating is disbonded, then these techniques are not effective. effective. Sorry. Now, direct examination, like just covering few slides, like in addition to ILI, which I'm not covering today, there are the direct examination, like you have to make the bell hole. From the bell hole, we can check like if there is a real defect. So these are some examples where we did the direct bell hole inspection and we found there was a coating defect, and these photos were taken. Similarly, this is the verification of DCVG fault, IR severity 32%. So we found these kind of defects there, just like a direct assessment. Like the message is only indirect like assessment is not enough. We have to have certain direct assessment as well. This is the message. Here, verification of DCVG fault IR severity 32%. If you can see that example of loosely bonded coating, scaling developed underneath the coating. Then here, example of disbonded, like if you see there's a clear gap on the bond here. The coating is above the pipe and pipe is separate. If there would be any corrosion underneath, nobody can prevent it. Then example of disbonded coating again, like here you can see this blister. This is one example where bond is like a coating is disbonded. Like there could be like in marshy areas, if there could be bacteria, then this could also be the scenario where coating is eaten up by the bacteria. Here you can see the example of SRBs in the marshy areas where bacteria does exist. So then there could be a wrinkles or bagging, crown cracking in enamel coating caused by the soil stresses. These issues are also there in certain areas. Then evidence of poor coating in the Grethfeld. If you see this, coating was not so effective here, and it means it may be a weak area where high corrosion can take place. So how to classify the fault location? There is a criteria given in 502. So I'm unable to go through that criteria because of time limitation. So here, like how to classify the fault locations, low, medium, high categories are there. These are based on the IR ratio of DCVG, or if a CIP data is shown, like the voltage potential -8, 50 millivolts, then IR ratio less than 15, and the source resistivity should be 50 to 100 ohms per meter. So these are the criteria which should be followed while classifying the defect location as an indirect assessment. Then direct assessment goes there. So here, like example, how to classify multiple like indications: DCVG survey coating defect, CP survey pipe potential, ACVG survey defect intensity, soil resistivity, which is like greater than or 500, less than 500 ohms per centimeter, pipe depth, earth cover less than 0.5 meter. Right. These are the basically certain criteria for the defects. Then how to classify fault location? Again, use a combination of these, like W is equal to 3A plus 2B plus C, mean like the indication shall be classified as a severe, and if W is 6 minus 11, indication shall be classified as a moderate, then less 6, the indication shall be classified as a minor. So all these combinations are, then we use that, like weightage factor A, B, C, minor, moderate, and severe, and this is the combination 3A plus 2B plus C. This way we classify the fault locations. So last part, like we use all this information was basically imported into the whale plant, Velosi whale plant software. So here is the data. I will go to data direct. Like this is the DCVG, if you can see, DCVG survey result. This is a record, and we can get the report also. Then here we see metal losses for the direct assessment, where this is a pipeline route, it is a defect, and a whole pipeline can be seen. I'm just showing you one portion. Then this is the basically ACVG survey, and along with the pipeline, by the report we can see the complete pipeline data. Then this is the CP reading across the pipeline route, whether the value was less or more than the potential data. Then this is the closed interval potential survey, the CP readings across the pipeline. And if we have to combine three, and like a survey result, we could see that. This is the one of the report of DCVG report. This is the CP report from the whale plant for all the locations. Then, like, next thing was the remaining life calculations, definition of reassessment intervals, assessment of ECDA effectiveness, modification criteria. Then, like a maximum flaw size, how should be calculated? Then predicted failure pressure by using the reference standards like all string ASME B31.31G modified 31G methods. Here, like as we like normally do, factor safety FOS of pipeline is given as FOS is equal to FP over MAOP. Design factor of the pipeline is given as a DS, MAOP over FP. Then where FP is the predicted failure pressure, in general, if FP failure pressure is less than MAOP, immediate recommendation is there, remediation is required. If FP is greater than MAOP, then scheduled remediation can be acceptable. If MAOP is FFP is greater than MAOP or FOS is FP over MAOP is 1 greater than 1.39, monitored for possible future remediation. This is the criteria what we used. So MR is equal to normally, MR means reassessment interval, half of calculated remnant life. Then different ECD region may have a different RA interval. For liquid pipeline, maximum 10 years. For gas pipeline, generally 7 years. I will not these are the conclusions, but we found different defects like DCVG 146 coating defects on average of 180-meter interval of the pipeline span. Then CP potential not meeting criteria of minus 850 millivolt IR free potential. Then one CP station ground bed resistance too high at 4 ohms. So this kind of recommendations or gaps were identified for each section. Then also findings and recommendations were made. So I cannot go through all this because of time limitation now. Here, this is a DCVG report and SIP survey report, what we submitted. So this is just a recapping. For any indirect assessment, we have to go pre-assessment, indirect assessment, direct examination, and post-assessment. So we have gone through the whole process. Our main focus of today was indirect inspections. Then direct assessment covers hydro testing, inline inspection, and direct assessment got when we say direct assessment, one is the ECDA and then also direct measurement of the thicknesses. See here, what is the control of the external corrosion? We have to have a protective coating. We have to have a cathodic protection. We need to maintain the operation within the operating envelopes and as per the operating philosophies and manuals. Then we need to test and monitor the situation. We need to do the maintenance for the CP system, TR units. We need to monitor the test point of the CPs whether potential CP is being provided and maintained. Now, last part, where then I will take the questions. So here, which of the following failure mechanism is classed under the time-dependent threats in pipeline integrity management? Which of the following, we read earlier, just to check your memory, which of the following failure mechanism is classified under the time-dependent threats in pipeline integrity management? And answers are option-wise: gasket o-ring failure, external corrosion, vandalism, incorrect operational procedure. The mostly answer is right. It's a B, external corrosion. One more question before we take your questions. Which of the following are steps of direct assessment ECDA? If you can remember, external corrosion direct assessment is not a direct assessment, it's external corrosion direct assessment. There is also ICDA, internal corrosion direct assessment. There is also a standard of NACE, which is called SCCDA, test corrosion cracking direct assessment. So here we're talking about external corrosion direct assessment. So the answer is everybody's giving right. But yeah, one guy said, Carol Femi, it's not B, it is E. All of above. Pre-assessment is required, indirect inspection is required, then direct examination is also required, then post-assessment is also required. This is a part of basically ECTA. So thank you very much for your time. So I was in between 4 o'clock. I tried to complete because target was 4 o'clock. So now we'll take a few questions to answer. And so Mr. Abdullah, over to you. And we can give the platform to our participant to ask questions. Okay?
Okay. Mr. Daniel Luces has already asked a question. So, Mr. Daniel, we are giving you access to your microphone. Please unmute and ask your question.
I can read your question. Thanks for asking this question. The stray current can comes in like if you have insulating joints, and if the both insulating joints like flanges, insulating flanges, if they are not connected by earthing wire, then there could be a potential stray current between the two flanges. So that is the location where stray current can come in the pipeline. Thank you. Go to next question, please.
So, Mr. Anala Appala Ravi Kumar, we are giving you permission to talk. Please unmute and ask the question.
The question.
Good evening, sir.
Good evening.
Sir, what is corrosion coupon and corrosion probe, sir? Where
Yes,
it is
thank you.
and why?
Yeah, thank
Okay,
you very
thanks.
much for your question. This question, like the corrosion coupons and corrosion probes, are installed to measure internal corrosion. These are part of ICCDA, internal corrosion, ICDA, internal corrosion direct assessment. Like if there would be, like there are two kind of probes which are normally used. One is a weight loss coupon, and second one is ERP probes, electric resistance probes. See, weight loss coupon mean if there would be weight loss of those coupons more than the expected range, it means fluid is more corrosive. And if we are losing the coupon's weight, it means there would be also corrosion in the pipeline. This is an indirect assessment of the corrosion in the pipeline. ERP probes are normally electric resistance probe. If a fluid is supposed to maintain certain resistance, if any corrosive element will come, so it may have more corrosion or more aggressive corrosion. So it means that we need to take the corrective action. So both probes are part of ICDA, not part of ECDA, sorry, not ECCDA. Okay, sir. Thank you.
Okay.
Okay,
Thank
sir.
you,
Thank
sir. So now we will move on to the next question. Mr. Srinivas Ambadi, we are giving you the permission to talk. Please unmute yourself and ask the question.
Yeah, good evening. Thank you very much for this wonderful session. I just want to ask whether this Stupak or Denso type of wrapping, will it be more better option comparing with the simple coating like 3LPE and others?
See, in general, there are three types, like we said earlier. One is bitumen, second is epoxy, third one is three-layer polyethylene. And these like wrapping, this is a compromise. So I'm not so sure if these coating could be better than the three-layer polyethylene. But three-layer polyethylene and HSS sleeves, that is a combination nowadays being used. So I'm not sure if these would be better than the three-layer polyethylene or not. But general practice within the industry is nowadays three-layer polyethylene. This could be for the joints and maybe for short period. I'm not so sure about it, sir. So I have to say that.
Yeah.
Thank you.
Fine. Thank you.
Thank you, sir.
Thank you, Mr. Srinivas. Now we will move on to the next question. So, Mr. Zafar Khan, we have given you the permission to talk. Please unmute yourself and talk. Ask the question.
Okay. The question is how does how we choose where DCVG is required and where ACVG is preferred. Basically, general technique is DCVG. ACVG is required in the hilly or the rocky areas, and it can help. So DCVG is more prominent, and it is followed up with ACVG and SIP surveys. So thank you very much, and you can contact us if you need more answers or you have some more question to be asked. We would be happy to answer you. And sorry for there was interruption in between due to technology. So thank you very much, and we look forward to meeting you next webinar on some other topic. Thank you.